Hi, I'm David. The common rail diesel engine we're going to be using today is the GM 2.2 litre Family Z engine, as fitted to the Theta platform, Captiva and Antara. The schematics apply to this vehicle, but are common to many CRD engines. Make sure that you have the correct schematic when working on your engine. This module is designed to give you a good understanding of the electrical side of the common rail diesel. The electrical inputs and outputs can be put into various groups: sensor inputs, switch inputs, injector control, actuator control, relay controls, lamp controls, and communications. The sensor inputs are intake air temperature, mass airflow, engine coolant temperature, fuel temperature, barometric pressure, boost pressure, accelerator pedal position, exhaust gas recirculation position, throttle position, crankshaft position, camshaft position, fuel rail pressure, vehicle speed, differential pressure, exhaust temperature, NOx sensor, oxygen sensor, intake runner control, turbocharger vane position sensor, water and fuel sensor, and the battery. We'll look at the function and operation of each of these sensors one at a time. The inlet air temperature sensor, or IAT, is part of the mass airflow sensor. It is a negative temperature coefficient thermistor. Information from the IAT is used to help determine air density. Airflow is measured by the mass airflow meter, or MAF. Combined with the IAT, the total density of the air entering the cylinders can be calculated. With this information, the ECM will know the maximum amount of fuel that can be injected into the cylinders. It will also be used in determining EGR operation. Here is a typical oscilloscope pattern for a mass airflow sensor. The engine coolant temperature sensor is used to adjust the fuel injection quantity and to provide information for the glow plug operation. Like the IAT, it is a negative temperature coefficient thermistor and uses a typical 2-wire sensor circuit. Fuel temperature will determine if the fuel heater needs to be turned on. This data will also be used in determining glow plug operation. The fuel temperature sensor and the fuel heater are in the same housing, which is mounted in the fuel filter. Barometric pressure is used to determine actual boost pressure. The ECM subtracts barometric pressure from manifold pressure to obtain the true boost reading. At key on, the readings between the boost sensor and the baro sensor are compared for validation. The baro sensor on this engine is mounted in the ECM. Intake manifold pressure and temperature are combined in the one sensor. Once the intake air pressure is boosted by the turbocharger, it increases in temperature. The intercooler will decrease the temperature and also the pressure. Boost pressure combined with air temperature can now be used to calculate the mass of the charged air to determine maximum fuel quantity. The accelerator pedal position system, along with the engine control module, is used to calculate and control the amount of acceleration and deceleration by controlling the amount of fuel delivery. The sensor is made up of 2 individual sensors within the one housing. 2 separate signals, low reference and 5-volt reference circuits are used in order to interface the accelerator pedal sensor with the ECM. Some APP sensor signals will read in the same direction with the same voltage. Others will read in the same direction with different voltages. and others will read in opposite directions. Exhaust gas recirculation is very important on diesels. This is due to their high combustion temperatures, which produce an excess of oxides of nitrogen, or NOx. The ECM uses the EGR position sensor to determine position of the EGR valve. A variable voltage signal based on the EGR valve position is sent from the sensor to the ECM through the EGR position sensor signal circuit. Here is the feedback signal from the EGR position sensor. The throttle position sensor gives feedback to the ECM about the position of the throttle butterfly. This will confirm that the butterfly has moved to the required position. The sensor is mounted in the same housing as the throttle position motor. Crankshaft position and speed information is sent to the ECM from the crankshaft position sensor. This is a 3-wire Hall effect sensor. The crankshaft position sensor can be used on some engines for zero fuel correction and/or idle vibration control. Zero fuel is the time during which the injector is activated, but without any fuel coming out. Zero fuel correction is learned from calculations based on signals from the crankshaft sensor. During overrun mode, a short injector activation is performed briefly. The duration gradually increases until the injector activation is detectable by the crankshaft sensor. This value is saved and used in all subsequent normal injections for more precise control. Idle vibration control reduces engine vibrations caused by torque variations between the cylinders. These variations can be caused by differences in fuel injection quantity or injector performance. The ECM corrects the injection fuel volume between cylinders based on the revolution signals from the crankshaft position sensor. Cylinders producing more crankshaft acceleration will receive less fuel, and those producing less acceleration will receive more fuel. The ECM correlates the crankshaft to camshaft position so that it can determine which cylinder is ready for injection. Here is the relationship between the crankshaft and camshaft sensor. The fuel rail pressure sensor gives the ECM an indication of fuel pressure. The ECM uses this information to regulate fuel pressure by commanding the fuel pressure regulator open or closed on the inlet of the fuel injection pump. A differential pressure sensor is connected across the diesel particulate filter and provides feedback on soot level or exhaust back pressure to the ECM. The differential pressure sensor measures the pressure difference between the entrance and exit of the diesel particulate filter. The exhaust gas temperature sensor is a variable resistor that measures the temperature of the output of the engine exhaust and the inlet to the DPF. 2 NOx sensors are fitted to this engine. They're used to help the engine idle quieter. When the NOx threshold is reached, the ECM will adjust the pilot injection at idle in an attempt to reduce the noise. A wideband oxygen sensor is provided on this engine to assist in the reduction of emissions. The position of the port deactivation or swirl control is sent to the ECM from the intake manifold tuning valve sensor. This is a 3-wire sensor containing a variable resistor. Vehicle speed is obtained from the high-speed bus. This engine uses a variable vane turbocharger. The vane position is reported to the ECM by the turbocharger vane position sensor. The water in fuel sensor detects an excess of water in the filter system. A ground is sent to the ECM when the level is exceeded, and a water and fuel light will be illuminated in the instrument cluster. The switch inputs include ignition, clutch, brake, neutral, and cruise control. In the fuel injection control group, is the fuel pressure regulator and the injectors. The ECM receives pressure information from the rail pressure sensor. The fuel pressure is controlled by the fuel pressure regulator, which is located on the inlet side of the fuel injection pump. The more fuel that is allowed into the injection pump plunges, the higher the pressure. This is single-point control. Engines that use a two-point control will have a fuel rail pressure control valve that can be opened to control the high-pressure side of the system. The injectors deliver several small quantities of fuel, known as pilot injection or pre-injection, and then the main injection quantity. This gives us a saving in fuel and a reduction in emissions that was not available in the old mechanical systems. I have an oscilloscope connected to one of the injectors. Let's have a look at the pattern. With the engine running, you can see the pilot injection pulses and the main injection pulse. I'll just pause the waveform and have a closer look. After the initial opening, the voltage is pulse width modulated until the injector is closed. This is the same for pilot injection and the main injection. Measuring each of the pilot injection pulses, you can see that they range from 309.9 microseconds to 314.6 microseconds, or 0.307 milliseconds to 0.314 milliseconds. The main injection pulse is 605 microseconds, or 0.6 of a millisecond. Some CRD engines remove one pilot injection pulse as RPM increases. This more precise control of the injection process helps to reduce noise, produces lower emissions, and gives us better fuel economy. Under actuator controls, we have throttle body, exhaust gas recirculation, intake runner control, and turbocharger vane control. The throttle body motor is controlled by two bidirectional drivers, allowing the motor to operate in either direction. The default setting for the throttle butterfly is wide open. The butterfly partially closes under EGR operation to create a low pressure area to assist the flow of the EGR gases. When the engine is turned off, the butterfly shuts momentarily to prevent any run-on. Remember, this is a diesel. The throttle butterfly does not restrict the amount of air going into the cylinders to control engine speed. This is done by the amount of fuel injected. The ECM will operate the EGR solenoid when certain operating parameters are met. These parameters will vary from manufacturer to manufacturer. This engine must be idling or under cruise conditions. The intake air temperature must be more than 5 degrees C. The engine coolant temperature must be between 60 and 96 degrees C, and the barometric pressure must be more than 74 kPa. When the EGR solenoid is operated, the throttle butterfly will close slightly to create a low pressure area. The mass airflow sensor should now see a reduction in airflow due to the incoming EGR gases. If there is no reduction in airflow, then the butterfly will close more and the EGR will be opened more. This process will continue until the ECM decides that there must be a fault in the EGR system. A DTC will then be logged. EGR control can be by direct electrical operation, as it is in this vehicle, or via electrically controlled vacuum solenoids. There is also an EGR cooler to reduce the temperature of the gases before entering the cylinder. The EGR cooler bypass is controlled by the EGR cooler bypass solenoid valve, operated by the ECM. Intake runner control on this engine is done by port deactivation. This is also known as swirl control. There are two intake ports for each cylinder. At low RPM, one of the ports is closed off by a butterfly valve. As the engine speed increases, then the closed port is progressively opened. This ensures that there is adequate swirl in the cylinders at all times. The variable turbocharger vanes are controlled by the turbocharger vane position control solenoid. The ECM will vary the boost depending upon the load requirements of the engine. The turbocharger vanes are normally open when the engine is not under load. The ECM will close the turbocharger vanes to increase the engine power and to create a higher pressure. The ECM will often close the turbocharger vanes to create back pressure to drive exhaust gases through the EGR valve. In extreme cold temperatures, the ECM may close the turbocharger vanes at low load conditions in order to accelerate engine coolant heating. The ECM may also close the turbocharger vanes under exhaust braking conditions. Turbocharger vane control can be via direct electric motor operation or via an electrically operated vacuum solenoid, as it is in this engine. Glow plugs are used to heat the combustion chambers of diesel engines to help with starting. The glow plugs are switched on prior to turning over the engine to provide heat to the combustion chamber and remain on as the engine is turned over. Once the engine is running, the glow plugs are no longer needed. Although some engines run the glow plugs for between 5 to 10 seconds after starting to ensure smooth and efficient running, and sometimes to keep the engine within emission regulations. Control of the glow plugs is accomplished by a glow plug control module. The temperature and power consumption is controlled between the ECM and the glow plug controller. Each glow plug is energised individually, keeping pre-glow times to a minimum, increasing glow plug life. As the glow plugs heat up, their resistance increases and the current draw decreases. Some glow plug control modules are incorporated in the engine control module. The electric fuel pump is usually operated by a relay circuit controlled by the ECM. The fuel heater is also turned on by a relay controlled from the ECM. As I mentioned earlier, this will only operate in very cold climates. Much of the information for the electronic controls is carried via the Controller Area Network, or CAN. The ECM is also responsible for illuminating the engine check light for emission DTCs and the glow plug light during glow plug operation. There are many sensors and controls in a modern common rail diesel engine. Knowing how these work will always give you an advantage. This module was designed to give you a comprehensive understanding of the electrical features of common rail diesels. And remember, training is the key to your success. Bye for now.